Alright, now for exercise 21. I've done my best to fit everything on one screen and try to make it more compact. So despite Folland's efforts of trying to make this exercise as large as possible in the textbook by splitting up between 2 pages, I think I've managed to kind of keep it sort of compact here. So we're basically just going to follow his hint here, but it's still going to be a little tricky. And it's certainly going to be longer, but I'm sure you realize that because you can look at the time thing on the side that tells you how long this video is going to be. I, however, do not yet know how long it's going to be. So, let's prove this. So, let E belong to script M. Then this set, the sum nu of Ej, E equals disjoint union from 1 to n of Ej. Well, this is certainly it's a subset of 1 to infinity of nu Ej equals 1 to infinity because, well, if you allow, yeah, it's obvious. This one we go to infinity, and here we just go up to a finite number. But then, what's another way of writing this? We could also write this as the sum from 1 to infinity of the integral over the set Ej of just d nu, or you could write like 1 d nu, like the function that's constantly not 1. I'm just going to leave it blank. I don't want it to look like an absolute value sign because we have an absolute value sign there. This is, of course, again, E equals disjoint union of 1 to infinity Ej. But certainly, these functions, these constant functions, 1s are always less than or equal to 1, and so this is a subset of, let's see here. Well, because these are disjoint here, we could write this, we could basically bring this sum inside here, and it would be fine because all of these Ej's are disjoint. And so then it would be in this form, f d nu, where f is less than or equal to 1. And this is because, if you were to actually take this sum inside here, what you would end up with is you would end up with the sum of the indicators of the Ej's, and that's just going to be equal to the indicator of E, which is certainly going to be a function that's less than or equal to 1. And so, hence, well, if you look at what this means, this literally means that taking the supremum over these sets yields that mu1e is less than or equal to mu2e is less than or equal to mu3e. So that's basically the easy part of this exercise. So now what we want to do is we want to prove that mu3 is less than or equal to mu1. So next, let f be a function whose f is less than or equal to 1. By the way, note that f is in L1 nu because, let's see here, just the function here, let me just write as this, the integral over the entire space of the function that's constantly 1 d nu, this is equal, and let's take this as an absolute value, this is equal to nu of E, and that's less than or equal to absolute value of nu of E. And this here is by proposition 13 point something. I'm pretty sure it's 13.a, but whatever it is, you can bring this absolute value inside. But then this is going to be less than or equal to norm, the total variation of nu evaluated on the whole space, but that has to be finite because nu is a complex measure. that's one of the things that makes complex measures really nice to work with, is that they're always finite. And we're going to exploit this a lot, so it's worth noting here, and we're going to use this throughout the exercise. So now, I claim that the integral over e of f d nu is less than or equal to the supremum of sum from 1 to n of nu of ej. E equals disjoint union 1 to n of ej. So basically, the mu1 norm here. And I just wrote it out because we're going to use this explicit form. So, see here. Since do we assume that f is measurable? No, but I mean, basically here, I mean, you're assuming that f is measurable because otherwise this wouldn't make sense. Oh, that reminds me. There's another error in Folland. That mu should be a nu. Or maybe that might be an error just in the copy of Folland that I'm using. Whatever. If it's not a nu there, then it should be a nu. I guess they fixed that in the new version. All right, I'll stop that. Since f is measurable, I'll just write it like that. There exists Sn, which is a sequence of simple functions such that Sn in norm Sn increases to f, and then Sn goes to f point wise and uniformly. Why are we able to get uniform convergence? This is because f is bounded. And so let epsilon be greater than 0. Right. Choose some Sn such that the uniform norm of the difference between these two is less than epsilon over total variation of nu of our set E. Now here, of course, I just mean the uniform norm, meaning like the supremum overall. That's like the supremum overall x of fx minus snx, in case that wasn't specified. I guess this is section 3, or this is from chapter 3, which I think the notation of like this subscript for the uniform norm comes a little later in the textbook, if I recall. Maybe in chapters 5 or 6. I don't quite remember how it works, but that's just in case it wasn't clear. And again, why is this okay? Well, actually, I guess you want to be careful about the case where E has measure 0. Typically, that doesn't cause us issues, but let's do a neat trick here. Let's just add 1 in that denominator, just in case. And we also know that this is not, like we're able to divide here, this is not going to be infinity, so this is not going to be 0. Or whatever, it's fine. It works fine. So, anyways, then I'm not going to write out, but we're going to use the reverse triangle inequality a lot. Then we have, I'm going to have to scroll down here a little bit. Oh well. So then we have, what do we have? We have the integral of e of f d nu minus the integral of e of Sn d nu. Well, this is going to be less than or equal to the integral over e of f d nu minus the integral over e of Sn d nu, just combining everything. Because the normal reverse triangle inequality works with the absolute values on the outside here, but in this case it doesn't really matter because it's like if you were to write this here, then if you were to remove these, then either this is going to be a negative thing, in which case this inequality is trivial, or it's going to be positive, in which case it's the actual inequality you're looking for. Don't worry about it. It works. Trust me. Or rather, because this is mathematics, don't trust me, but justify it yourself. So this is equal to integral over e of f minus Sn d nu, which is combining these. And by proposition 13c, this is integral over e of, or less than or equal to, integral over e of f minus Sn d nu, just bringing the absolute values inside. And then what is this less than or equal to? Well, we assume that the uniform norm of this is less than epsilon over, the thing. So this is going to be less than or equal to, let's see here, epsilon. Here, let's write it out. Integral over e of epsilon over nu of e plus 1 d nu. But this is a constant that's just going to come out. And so what we're going to get is when this constant comes out, what's left is the integral over e of d nu, and that's going to be just the nu of e. But that's going to cancel with this thing, and so what we're going to end up with here is that this is less than or equal to epsilon. Maybe it's strict inequality, I don't really care. So now if we bring this guy onto the other side, what this says is integral over e of f d nu is less than or equal to the integral over e of Sn d nu plus epsilon. Epsilon greater than 0 was chosen arbitrarily. And so basically, no matter what epsilon you give me, we can make this inequality as sharp as we want by choosing a sufficient simple function here. And so, yeah. And so now what we have is, let's see here, and so that gives us exactly what we want. F d nu is certainly going to be less than or equal to the supremum over all such things of this form, integral over e of Sn d nu. And just say like Sn, well, we know what the assumptions on the Sn's are because we constructed them, so we're fine here. But now these, if you look at these Sn's, what do these look like? This is like the supremum over all integral over e of, I should probably start this on the next line, equals supremum over the integral over e of the summation of, say, from 1 to n, and this n depends on this capital N, so it's n sub n, which is perfect notation. So this is 1 to n sub n of, say, like constant ci times the indicator of ei, and you know how these simple functions work. The ci's are constants and the ei's are disjoint subsets. But because the SNs increase to F, we know that these constants always have to be less than or equal to 1. And so basically another way of writing this would be just the supremum overall. You could just write this as the sum from 1 to n of the indicators of the EIs. But then you can just bring the sum outside, and so you've basically got the absolute value of the sum from 1 to an n of nu of EI. But now if we bring these, we just do the normal triangle inequality, this is going to be less than or equal to the supremum of all sum from 1 to, say, now let's just call it n, n of the value of nu of EI. And this is precisely equal to, what is it, nu 1? Is that? Now I have to scroll all the way back up to make sure that this was exactly what we wanted. Yeah, this is exactly what we wanted. Mu 1 of E. So what does this, so we have this thing is less than or equal to this. This holds for all such F, and so the supremum over all integral over E F d nu, F is less than or equal to 1, is less than or equal to mu 1 of E. So thus, well, that's precisely mu 3. So mu 3 of E less than or equal to mu 1 of E, and hence mu 1 of E is equal to mu 2 of E is equal to mu 3 of E. And so that finishes part of the problem. We still got a bit to go. But yeah, I'm probably gonna just like pause this and make sure that everything got recorded fine, and then erase this all and give you the proof of the next part of this. Alright, everything was good with the first part of the recording, so let's continue. So let's just summarize. We now know that for all E, or, so yeah, so for all E and M, mu 1 E is equal to mu 2 of E is equal to mu 3 of E, i.e. mu 1 equals mu 2 equals mu 3. I now claim that mu 3 is equal to the total variation of nu. So again, let E be in script M. So let one direction will be easy and one direction will be less easy. Well, if you have two directions to go, one is always going to be strictly less than or equal to the other in terms of easiness, but as in this case, sometimes one is notably more difficult to prove than the other. So let F be in here such that norm of F is less than or equal to 1. By 3.13c again, we've got integral of E of F d nu is less than or equal to, you just bring everything inside, not just to F but to the nu, and this is certainly less than or equal to nu of E. And so certainly this means that supremum over all of these things is less than or equal to nu of e. Now, we want the reverse inequality. So, for the reverse inequality, now we're going to show a function that gives us the inequality in the other direction. And let's see here. Actually, let me look at my notes real quick. We might actually get equality. In either case, it'll get us what we need. Right, so we want to choose a function that does the reverse thing. So basically get a function that kind of, I don't know, sort of like you have to choose the right one of these to make it not just less than or equal to, but to make it equal to. And it turns out that it's not quite intuitive how you would come up with this function, but let's see how it works. So for the reverse inequality, note that nu is absolutely continuous with respect to the total variation of nu, and that's by 3.13b. So we can define the Radon-Nikodym derivative of nu with respect to nu. And we'll call it f is equal to d nu over d variation of nu. So by 3.13a again, if we look at the absolute value of f, this is just, let's see here, this is d nu over d nu. But again, we've got, like, up on top here, we've got the absolute value of d nu, and so that's going to equal d nu, or less than or equal to d nu over d nu, which is equal to 1. This inequality here is by 13 point, whatever it is, 13a, whatever, because you've got the nu of e is less than or equal to the total variation nu of e. Now this notation is just kind of like a compact notation. You should write this out and really understand what this means. But this inequality does work this way because of exercise 13. So this is equal to 1, and by 3.13b, f is equal to 1 almost everywhere. Let's see here. So since norm of f is less than or equal to 1, norm of the complex conjugate of f is less than or equal to 1 as well. So then, by the chain rule, we have, and for the chain rule, if you don't quite remember how that goes, look in the proof of theorem 12 or 3.12, whatever the 12th theorem in this chapter is. And I think that's the general Radon-Nikodym theorem, or like decomposition, whatever. But it'll explain the chain rule if it's not on the top of your head. So, on the top of your head, at the top of your head, whatever. So if we calculate this, we just write this as, well, the integral of e of f hat of d nu over d total variation of nu, and times that. And since we're integrating with respect to a positive measure now, I'm not going to write the absolute values on the outside. So this is integral over e of, and what's f conjugate. That's just d nu over d nu, this whole thing conjugate. D nu. Actually, no, that's not the best way to write this out. The best way to write this out is f, and then you notice that this thing is equal to f, d nu, but this is just f squared, absolute value of f squared, d nu, and f is equal to 1 almost everywhere, so this is going to be equal to the integral over e d nu is equal to, let's see if I can fit it on here, integral of nu of e. There we go. So absolute value of nu of e, let's see here. So yeah, so we have this equality. So this is equal to this, and this is certainly less than or equal to the supremum over all such things. So yeah, I guess I haven't quite reflected on why this function should maximize the value of these things and get us to obtain this maximum value. But I mean, just looking at it, it works. So, but what does this mean? This is exactly the inequality in the other direction. So, thus, nu of e is equal to mu3 of e. And so, nu is equal to mu3. Hence, mu1 equals mu2 equals mu3 equals total variation of nu. And this finishes the proof. Once I rewrite this nu in a way that looks like a letter.